Good evening, everybody, and welcome to the Royal Astronomical Society, and thank you for coming out on this beautiful spring evening. It is my great pleasure and privilege to introduce tonight's speaker, who is giving the Caroline Herschel Prize Lectureship, which was established by what is now the Herschel Society in association with the Royal Astronomical Society, to celebrate Caroline's memory by supporting promising young women astronomers early in their careers. Caroline Herschel, William's younger sister, started out as his assistant, but in time became recognized as an important astronomer in her own right. She was the first to be paid as such and was awarded the Society's Gold Medal in 1828. Our speaker this evening is Dr. Heloise Stevance. She is in her second postdoc at the University of Oxford after several years at the University of Auckland, and she began her work in observational astronomy with spectropolarimetry. There's a word to test me in the evening. Thank you. Her PhD, and then became an expert in theoretical population synthesis in Auckland, and is now an independent fellow applying machine learning techniques to time domain astronomy as a Schmidt AI in Science Fellow at the University of Oxford. And her talk this evening is, well, I think you can read it for yourselves. How can AI help us find exploding stars and hungry black holes? Please welcome Dr. Stevance. Thank you.
Thank you for the introduction. Thank you for coming. So to do astronomy, you don't need fancy equipment. People successfully sailed the Pacific with nothing but their eyes and the knowledge of the stars. That being said, with new technology, we can open a new window into the universe. And a first example, need the mouse on the right screen. A first example of that is a telescope, which allowed Galileo to find the moons of Jupiter. Then, with the invention of photography, astronomy really came into the Industrial Revolution, and we started being able to survey the sky on a level never imaginable before. In the second part of the 20th century, we invented, not astronomers, but humans in general, invented semiconductors. Semiconductors allow us to control the flow of electricity on a really small scale. And they also allow you to turn photons into electrons, to turn light into electricity. That's basically the digital camera. In the second part of the 20th century, we also started to master rocketry. And with rockets, you can send out artificial satellites, and you can send your telescopes out into space above the atmosphere. The atmosphere is the big, beautiful blanket that protects us from some of the harshest radiation in the universe, but it also makes us blind to some of these beautiful colors, and it gives us a bit of a blurred view. I think one of the best examples of how beautiful the universe is when you don't have the atmosphere in the way is the Hubble deep field and the ultra deep field. Here you've got a really tiny portion of the ultra deep field, which I think this is roughly 100 times smaller than the moon. The ultra deep field on its own is 10 times smaller than the moon, but the picture is massive. If you go to Wikipedia, you can download the full thing. And it's a patch of sky that astronomers thought was basically barren. No stars, no massive galaxies in the way. And they thought, what will happen if you point Hubble at that empty patch of sky for 1 million seconds? This is what happens. Beautiful, beautiful galaxies far out into the universe. Now, deep fields have become routine. When James Webb went up into space a few years ago, one of the first things it started doing was collect its very own deep field. And again, here you see a patch of sky about 100 times smaller than the moon and full of galaxies, some of them more distant than others. Now, the reason for this introduction is partially so I have an excuse to show some really beautiful pictures taken by some of our best telescopes, but also to impress upon you the fact that discovery in astronomy is the story of a partnership between people and new technologies. And that's the theme that I want to explore with you tonight. With my job, I'm very, very lucky that I get to travel the world. And last year, I got to visit the Heloise Observatory in Chile. It's over there. And where is my stick? The tin can you can see here is called the New Technology Telescope, the scale. And as you might see, there's quite a lot of clouds in that sky. So if you're an optical astronomer, not ideal. Fortunately, the clouds were very quickly blown away by extremely strong winds that started to batter the mountain and made it impossible for us to open the dome without damaging the equipment. So I was stuck on top of a mountain in the howling winds with nothing to do but play with my phone. And so play with my phone I did, and I took this picture of the Milky Way with this very phone that is counting down the minutes. Here you can see the center of our galaxy, the very bright bit there, and some cloud-like formations, which are clouds in the Milky Way, clouds of dust and cold gas. You might get a better view of this with this beautiful picture from an actual astrophotographer at ESA. And here you can even see colors in some of these nearby clusters. If any of you have been to a dark sky reserve, you will know that the night sky does not look like this to your eyes. That's because our eyes don't capture as much light as our cameras. When you're in a very dark sky, at best your eyes can see a few thousand stars. A telescope, like the kind of telescopes that I work with, can see 1 billion sources in their sky. It's a little bit difficult to grasp the difference between a few thousand to 1 billion, but I think we can do it if we think in terms of time, because that's something we experience instinctively. So a few thousand seconds is how long it's going to take me to deliver this talk to you tonight. 1 million seconds is roughly 11 days. That's how long Hubble pointed at the ultra-deep field. And 1 billion seconds is roughly my age, just under 32 years. So it's a lot of stars. The sky is very big indeed. So we have a big problem or a big challenge. That's more fun. Now, the sky is not only big, it's also ever changing. We've got things like shoulder of Orion. And here you can see a curve of its brightness changing over time. We've got things that are a lot closer to us, like asteroids and comets, that we can also detect in our sky surveys that are changing in the sky just because they're changing in position. And beyond asteroids, comets, and variable stars, we also have things much further away from us, like exploding stars in distant galaxies. We're going to cover some of these examples today, but not all of them in the interest of time. What I really want you to focus on in this slide is the timescales I've written there. So we've got days, weeks, hours, days, months. These are the sort of timescales on which these objects change in brightness significantly, change in appearance significantly. These are the sort of timescales we need to take new pictures with our telescopes so that we can study these phenomena. And what that means, because those timescales are so short, is that we need to keep mapping the skies over and over and over again. And that's the kind of capability we've only had as a species since the beginning of the 21st century. We do this with sky surveys like Atlas. This is not the only one, just the one that I work with, so that's the one you're going to hear about tonight. Atlas is the Asteroid Terrestrial Impact Last Alert System, and it is funded by ANSA primarily to find and track near-Earth asteroids, particularly the ones that could be dangerous for life as we know it. To do this, Atlas has 4 telescopes scattered across the world. We've got 2 in Hawaii, 1 in Chile, where I was this year, and 1 in South Africa. So having these telescopes in the northern and the southern hemisphere gives us a sort of 360 view of the sky. But like I said, it's not enough having a 360 view of the sky. You need to be able to take the pictures fast enough. So for our cadence to be sufficiently high, we need a large field of view. Here you can see a slightly overwhelming dashboard of one of the Atlas units. And here you can see the square in the sky. That's roughly, that is exactly the size of an Atlas footprint on the sky. That's the size of the picture we take. These three panels here are the last three images taken. And if you cast your mind back to the beautiful pictures of JWST and HST I showed you earlier, where I said the size of that picture is 100 times smaller than the moon. Well, the size of that picture could contain the moon many, many times. The moon is roughly this big in an Atlas image. And because Atlas has such a big footprint, we can go back to the same patch of sky every 1 to 2 days. So that's very useful to find near Earth asteroids, but it's also very useful to find things that go bang in the night sky. And because that's where I've come from as an astronomer, the things that go bang in the night sky is something I could talk about for a whole hour, but I don't have time to do this. So today we're going to focus on 3 kinds of explosions. The first we're going to focus on is probably one you've heard about before. It's the supernova explosion. The supernova explosion is something that astronomers discovered in the 1930s. And in the last 100 years, we've spent a lot of time and energy creating subclassifications of subclassifications of subclassifications, which we're going to completely ignore today and focus on 2 different types. There's only 2 types of supernovae tonight, the low mass stars and the high mass star supernovae. The difference between a low mass star and a high mass star is the mass they're born with. A low mass star is born with less than 8 times the mass of the sun. A high mass star is born with more than 8 times the mass of the sun. And the main difference between these 2 stars is how they die. The low mass star, like our sun, for example, when it reaches the end of its life, is going to leave behind something we call a white dwarf, a big ball of carbon and oxygen, roughly the size of the Earth, half the mass of the sun. And the white dwarf has a weird property. If it gets too heavy, it explodes as a low mass star supernova. And these supernovae create most of the iron in the universe and have really interesting properties that allows people to calculate the expansion of the universe. Someone got a Nobel Prize for this in 2011. Very important, but we don't have time to cover it. Now, the high mass star supernovae are the ones that I personally favor for completely subjective reasons. High mass star supernovae, first of all, look much cooler. They also create loads of really important elements for life as we know it, oxygen, calcium, all of that good stuff. And they leave behind neutron stars. Here you can see a neutron star. This is the Crab Nebula, by the way, in 5 different colors. This is not CGI. This is not AI. This is 5 different images from 5 different telescopes, including space telescopes. This is a very expensive picture. And the neutron star here is very interesting because neutron stars can go on to explode again as kilonovae. These are explosions we've only begun to explore as a field because the first proper kilonova was found in 2017. We've basically only got 3 of them at this point. Kilonovae are the merger of 2 neutron stars. This is an artist impression. And this can happen not because neutron stars are wandering the galaxy and suddenly colliding, but because massive stars are often born in pairs. And if you have 2 massive stars next to each other, and they both reach the end of their lives, explode as supernovae, and leave behind 2 neutron stars, you can have a binary neutron star system, which over time is going to spiral inwards. To understand why the neutron stars spiral inwards, we need to do a little bit of general relativity, but I promise it's going to stay at very low level. So you might have seen that analogy of the fabric of space-time as an actual piece of fabric that is taut. And if you have a ball, it creates a little well. And if you've got just one ball, that well is nice and round. But if you have 2 balls next to each other, 2 heavy stars, 2 neutron stars, that well is sort of peanut-shaped. And so as the 2 stars rotate around each other, they are going to wobble the fabric of space-time and send out waves, gravitational waves. We can visualize gravitational waves in this video because of the way that they distort the stars in the background. Now here we've got a neutron star orbiting around a black hole, and as the gravitational waves are emitted, the orbit shortens, get closer and closer and closer and closer together until eventually they merge and the gravitational waves go away. Now here we're going to have a look at another video, this time not about the gravitational waves, but about what happens to the neutron stars when they get too close to each other. Up, click, click. Here we've got two neutron stars in this simulation. We can't visualize the gravitational waves, but what we're going to be able to see is how the neutron stars, as they get really close, turn into that sort of teardrop shape and basically shred each other apart. So most of the material goes into that hypermassive neutron star, but some of it gets launched out into space. And that material is very hot, full of neutrons, and it is capable of making some of the heaviest elements in the universe: platinum, gold, rare earth elements that are in all of our phones. And it also creates a big bright light that we can sometimes touch. The final explosion that we're going, it's not really an explosion, bright thing we're going to look at is the tidal disruption event. That's where the hungry black holes of the title of this talk really comes in. That's what happens when a star gets a little too close and comfortable with a black hole and pays the price. Again, we're going to abuse videos of my delightful colleagues and the simulations that they've made. We've got a black hole here, interstellar-like. They don't always look like this. And here we've got a star coming in hot. And as it comes closer and closer to the black hole, it gets distorted, it gets spaghettified. But eventually, it gets so close and so spaghettified, it completely is pulled apart. Half of the material of that star gets flung out into space, half of it comes back towards the black hole. And if I pause it here, you can see this black hole has gotten bright. Of course, not bright. It's the accretion disk around the black hole. What you need to understand is that black holes are not magical space hoovers. Things don't magically fall into the black hole as soon as they get near it. It's a little bit like the hole at the bottom of your sink. If there is too much water, it's going to have to, spiral inwards, funnel into that sinkhole. Here, there is so much material trying to enter the black hole that there's essentially a space traffic jam happening. And just like real traffic jams, things get heated. And in space, when things get heated, they get really bright. Now, how bright and how that brightness changes over time depends on the properties of the black hole, how massive it is, how much it spins. And so this allows astronomers that care about these things to study black holes that would otherwise never be found. Black holes are particularly elusive because, one, you can't see them, two, you can't make them in the lab. So if a star is kind enough to make the black hole bright, we can learn a lot about this population. So hopefully by now it's clear why studying these explosions is interesting across many fields of astronomy. We can understand where we come from, we can understand kind of where we're going, and we can understand some of the coolest, hardest to study objects in the universe. But before we do this, obviously, we have to find these trending. All right, slight change of pace. Can you spot the difference between these two images? On the left and on the right, we have the same picture. It is a portion of the image of the Milky Way that I showed you earlier, the one that I took with my phone. The only difference between the two pictures is that one is the raw image taken from my phone, and the other one is the JPEG, so the compressed file saved from the raw image. If you know anything about JPEGs, you'll know that it's a lossy type of file compression. Basically, what you do is you take your original file, you do some maths, and you make the file much smaller, but in doing so, you lose some information. The problem here is that this picture is worse than this one. This picture, the lossy type of file compression, has higher resolution than the original picture. And that is not normal. That is weird. It means that something else happened. And what happened is that my phone is a smartphone, and my camera has software, and it can use magic maths to create new pixels. Essentially, it's using generative AI to make my pictures better, and all of your phones are doing it too. So what is AI? We don't have time to go into the whole history of what that word has come from. There's a long history that has more to do with people being people than with technology. But artificial intelligence is an umbrella term that has come and gone, and an umbrella term that has been used in computer science, statistics, philosophy, psychology. Basically, it's so broad that it is very devoid of meaning, unless, well, especially when you see it on LinkedIn. So for all intents and purposes today, AI is machine learning. It's the best way to think and conceptualize it. Machine learning is essentially statistics. I know now it sounds boring. I think that's why AI has caught on as a term, because it sounds so much more fun than statistics. But I promise, we'll make our computers do smart things anyway. So what we do with statistics to teach our machines to perform incredible feats is that we learn a function, a mathematical function. There's going to be no maths in this talk, but we have to use the concept of a mathematical function. And so what we're going to do is we're going to use an analogy. And the analogy is going to be a DJ deck. Now, you don't need to know how they work. I certainly don't. I've never used one of them. But conceptually, I understand that you put music in, you twist the knobs and dials, and a different sound comes out. That's basically what a mathematical function does. You put numbers in, you change parameters, different numbers come out. What happens with machine learning is that you have lost the manual, and you don't know what these knobs and dials are doing, but you do have data. So you've got examples of inputs, and you've got examples of outputs. And all you need to do is put the inputs in, change the knobs and dials until they look like the outputs, and you can learn how your function, how your deck works. This analogy is strongly inspired by an XKCD comic that came out 8 or 9 years ago, I believe, where we have a couple of stick figures, one on the ground saying, this is your machine learning system, and then one standing on a pile of math saying, yep, you pull the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? You just stir the pile until they start looking right. That is very accurate to what we're doing. But there is method to this madness. Now, if we think about the term AI in the way that we use it in society, I would say that it's more a reflection of your expectations of the machine than actually what it is doing. If you teach a computer to do something that people didn't expect it to do, people are happy to call it artificial intelligence. Until a few years ago, we didn't have ChatGPT-like systems, so we're happy to call it AI. But there are examples of machine learning that were science fiction until very recently that we now take for granted. And I think computer vision is a very good example of that. You take it for granted that Facebook can recognize your man in family pictures. You take it for granted that a speed camera can take a picture of your car, read your number plate, and send you a fine. You take it for granted that your phone can unlock itself by just looking at your face. And yet, it's only been a couple of decades since we've been able to do that. Computer vision has only got good in the 2010s. It started getting good in the 90s with LeNet, which is a specific kind of machine learning algorithm called a convolutional neural network. I can't explain how they work, because that would take the semester in an undergraduate degree. But all you need to know is convolutions, it's fancy filters, like the filters you put on your face, and in like camera, if you take a selfie, and the neural network is just a fancy maths function. And here we can sort of see how it works. We've got a first layer of filtering. We've got handwritten digits coming in. That's the input. That's the output. And you can see different filters make different edges of the number stand out, or the body or the outside. Now, as you get to the second layer of filtering, the numbers are still sort of legible by a person, but it's a lot more abstract. When we get to the third layer, completely illegible to the people, very abstract, but that's what's understandable by the machines. Essentially, these machine learning algorithms are ways to create abstraction in mathematical spaces so that the computer understands. Now, this is from the late 90s. That's why the GIF looks like this. That's why it looks so quaint. It's an original GIF from the 1990s. But things got a little bit quiet for convolutional neural networks until the 2010s, when a big data set was released by ImageNet. So that was 1.2 million images released with their labels. So the inputs and the outputs. The ImageNet people said, okay, go on, train your algorithms, and we'll have a competition, and we'll see if your machines can beat the humans. And beat the humans they did. In 2011, we had the first superhuman performance. In 2012, we had AlexNet, which won the competition by such a large margin. It really accelerated what we now call the deep learning revolution. And what was special with AlexNet is that it was very big. It contains 60 million of these knobs and dials, whereas LeNet, the one from the late 90s, only contains 60,000. And the reason I point out Facebook AI Lab here is because it's not the only tech giant that hopped onto the trend of machine learning in the mid-2010s, but it called its group of people or its research center the AI Lab. We think that's innocuous today, but back then the word AI was a bit of a black swan. Is that the right term? Like ugly duckling of machine learning, overpromised, underdelivered. In the late 20th century, no one was using the word AI. Facebook reclaimed it, and here we are 10 years later talking about AI everywhere. The reason things got really good in the 2010s was the perfect storm of access to data and access to compute. Historically, that's how machine learning breakthroughs have come together. For the data, it's pretty obvious that social media and the fact that we all had smartphones in our pockets for the first time in history gave us access to a large variety of data. For the compute, it's a bit less obvious unless you know that graphics processing units, GPUs, the things that gamers use, the things that CGI people use, are extremely good at linear algebra, the pile that the guy was standing on, the thing that machine learning needs. And so this put together made it such that computer vision was no longer the thing of sci-fi, but something that you take for granted and wouldn't even call AI today. But for astronomers, what that meant is that we could use magic maths to tell our machines how to read images and classify them, which is very nice because all we do all day, every day is look at pictures. Here is another game of spot the difference. Can you see the difference between the before here and the after? Can I even see it? Oh, maybe you can see it on the you can just about see that. I'm going to make that job easier. I'm going to remove the before from the after, and let's see if you can spot it. There it is. That blonde here is a supernova in a distant galaxy, and this game of spot the difference with the universe is what we do with Atlas. The problem is that difference imaging, this exercise of taking a reference image, removing it from an observation and getting the difference, goes wrong very frequently. So if you've got crowded fields like this, even if there's no difference, you can get a lot of false positives, of false alerts. In fact, every night we get of order 10 million alerts, but only a handful of real astrophysical events. The problem with a number like this is that it would take 6 months to a year to a single person to analyze the data for Atlas for one night. So what that means is we need to put our computers to work. We need to automate. Now, the first thing we're going to do with automation is not AI, it's not machine learning. We're going to do some basic cuts. First of all, we're going to check that things are bright enough. We're going to check that, so the Atlas, I forgot if I said this, when it points at a bit of sky in one night, it will take a shot 4 times separated by 15 minutes. It's good if you're looking for asteroids because you can see the asteroid go bloop, bloop, bloop in the pictures. It's good for us because we can say, okay, if the difference is only seen in one of those 4 pictures, it's probably not real. If it's seen in 4 or 3 of those pictures, it's probably real. So with those basic cuts, you can cut down on most of the garbage. The other thing you need to do, of course, is check for all of the variable things we know are supposed to vary. If you're looking for new supernovae, you don't want to find Betelgeuse every night. So we remove Betelgeuse, and then we're still left with thousands to tens of thousands of potential alerts. And that's where we need some fancier tools. We use a convolutional neural network on the difference images, so especially the center of that difference image. We put it through a CNN, and then out we get a number between 0 and 1. That's a real bogus score. If it's 0, it's bad. If it's 1, it's real. It can be any number in between. And what we say is that if the number is 0.2 or below, we put it in the bin. If it's 0.2 or above, we keep it in the stream. With this strategy, you can remove 98.5% of the garbage, which is really nice, but you're still left with hundreds of alerts, which eyeballers, that's a technical term, genuine. We put that in the actual papers. Eyeballers have to look at that data and make decisions every day. That's hundreds of order 200 to 400 alerts a day. And the reason that was the strategy for a long time, that's where it stopped, you still needed people, experts to look at that many images, is because eyeballing is complicated. It's a very complex task. It's also a very boring one. I forgot I had that slide. So 85% of what people look at is garbage. 5% is, and here you can see how biased I am, extragalactic transients, which I call good, and 6% is galactic transients, so real events, but that happened in the galaxy. Interesting for someone, but not me. So the problem with eyeballing, like I said, it's complex. You're not just looking at the picture, you're looking at a wealth of data. You're looking at pictures, you're looking at light curves, in this case, just one data point, just one detection, I should say, and a bunch of non-detections. You're looking at the location on the sky, you're looking at some contextual information. Did we find a source nearby when we did the cross-matching? How far is that source from the transient? You're looking at the scatter on the sky. And humans take this information and put it together with their expertise and use it to make really good decisions really quickly. And that's why it's difficult to automate. So what I did is I said, okay, what if our machine learning algorithm just followed the same strategy as the humans? The humans ask themselves two questions. Is it real? And if it is it galactic? And for doing this, I created something called the virtual research assistant. And the job of the virtual research assistant is not to replace the eyeballers. The eyeballers do three important jobs. They remove a lot of the garbage, and then they put the alerts into either the extragalactic or galactic category. When they put something in the extragalactic category, they also alert the other astronomers. It goes to another server and to another alert system. That's a lot of responsibility I don't want to put in the hands of the computer. So although the virtual research assistant follows the same strategy, it doesn't press the final buttons on the good in the galactic. Instead, it ranks and prioritizes the eyeball list, and it crops most of the bad. So that 85% of garbage, hopefully most of that taken care of by the machine. And what we get is an eyeball list that goes from hundreds of alerts a day to a dozen or a couple dozen. And it's been working. It's been working in production for a few months. And here is an example of last week. We've got the virtual research assistant doing its job in binning 83% of the alert stream that week. In color, we've got the labels given by humans. So that's data that the humans have handled themselves. You can see we've retrieved 6% galactic objects. 6% galactic objects, that's nice. You know, slightly lucky that week. 4% good, 5% good. Ooh, did we miss a few? No, it's not terrible. Last week was very bright moonlight, and so we find fewer good transients in bright moonlight. This is aggregated over several months. So it's working. It's brilliant. My friends and myself have to do only 13% of the work than we used to do. And the way it works is basically what I've told you this whole time. You take your inputs, which in this case is very similar to what the humans are looking at. You've got your big function that's been trained on data for which I had inputs and outputs. And we're answering the same questions that people would have initially. And so these questions for computer turn into a number. Is it real? Number between 0 and 1. Is it galactic? Number between 0 and 1. And so you can make a graph. I love graphs. So is it real? Is it x-axis? Is it galactic? I'm going to shout a bit more so that we might figure out. Is it y-axis? And so we can score our alerts on that 2D plane. Here you can see the blue stuff, the stuff I care about is in this corner, the real extragalactic. The galactic stuff is in this corner, the real galactic. But like I said, I want to rank the alerts. Don't want to just classify them. So how do you go from this scatter plot to a rank? Well, we use the newfangled technology of the Pythagoras theorem. We're going to just calculate the distance between our alert and the top rank. That corner, that's the corner I care about the most. The closer the alert is to that corner, the higher it is on the list. And as for the garbage, how do you garbage it? Well, if it's far enough from that corner, you just put it in the bin. And that's how you get something that works like this. You combine technology from 8 years ago and technology from 4,000 years ago, and you've got something that can do the job really decently. So I think we need to amend my statement earlier. New discovery in astronomy is a partnership between people and the right technology. The right technology does not have to be new. The right technology can be the Pythagoras theorem. If it works, it works. Right, so I could stop the talk here. I've told you that I did my job. The VRA works, bing, bing, bing. But there was AI in the title of the talk, and I've not mentioned ChatGPT. And I'm sure some people are getting itchy. So we're going to talk about ChatGPT and these large language models and why we have to be cautious in the next few years as to where we're going to apply them, whether we're going to apply them. Let's get to the last part of my talk. I promise I love artificial intelligence. It's starting to sound like I don't. I really, really like it. So can you tell me what this is? Can you see from just this part of the picture? I think I can help with a bigger part of the picture. That's an announcement board in an airport. Like I said, I travel a lot. I spend a lot of time in airports, sometimes more than others. That time I was in an airport for 12 hours because there was a strike and I was checking how late my plane was going to be. But I am a little bit blind and I couldn't be bothered getting up. So I thought I'm going to take a picture of the announcement board and zoom in and see what's happening with my plane. Unfortunately, when I zoomed in, I found what is essentially wingdings on LSD, and I couldn't read anything. Now, this is a problem, and it is just because my phone is smart, and it is caused by the same software that made my picture of the Milky Way so much more beautiful. But why did it scramble the words like this? Well, it's because this software is designed to make landscapes and faces more beautiful. Landscapes and faces, not very well known for having tiny detail made of straight lines and sharp right angles. Straight lines and sharp right angles are usually the pixels, the things you want to get rid of, the things you want to smooth out. So my software took this picture and made it beautiful and ruined the information I was actually looking for because it didn't know any better. Now, to understand why something like that can fail so catastrophically, I'm going to tell you about another little anecdote, another little machine learning breakthrough that happened recently. So in 2016, AlphaGo from DeepMind beat Lee Sedol at Go. Lee Sedol was the reigning world champion. And that was a big deal because, computers have been good at chess for like a few decades. Go is very, very tricky because it's got a lot more board positions. So that was a big deal. But what we're going to focus on is the fact that AlphaGo won 4 games and Lee Sedol won 1. Lee won 1 game because he made a decision that was unexpected by the algorithm. It was unpredicted. And when he did that, the algorithm started misbehaving, making really poor decisions, really, really stupid decisions. And that happens when you find yourself in a complete unknown in your machine learning function. So remember, we've got this big DJ deck. We're trying to figure out how the the different knobs work together. The problem is that if you've got millions, billions, or trillions of parameters in a function, you cannot fully explore how they all work together. Exploring how your parameters work together is a little bit like exploring a map. This is a screenshot of Civilization 5 for the games in the room. And in that game, you explore a map, and the bits of the map you've not discovered or uncovered are covered in this fog of war. Training a function is a little bit like trying to explore the map, and any bit of the map that you've not seen before is covered in that fog. And if the algorithm finds itself there, it's going to get lost. These areas of the map that have not been uncovered are called Sidolian voids by Neil Lawrence in his book, The Atomic Human. I cannot recommend it enough. And obviously Sidolian in honor of Lee Sedol, who beat AlphaGo for one of the games. And this effect is what you're seeing here. This algorithm is very, very effective, but not used to seeing these sharp angles, and it destroyed the one piece of information I was looking for. Now, this is a problem if you consider the fact that I care about the rarest and weirdest things in the universe. I am more likely than most to put an algorithm in an unfortunate position. So I'm very cautious about how catastrophically algorithms can fail when they're put in the unknown. The other problem with generative AI is that these are probabilistic models. So what that means is if you put the same number in, or the same input in, several times in a row, then what you're going to get out is slightly different every time. It's a problem if you don't know what the probabilities look like. And problem number 3 for large language models, they are not trained to be truthful, they're trained to sound human. They don't think, they're trained to sound human. They don't have logic, they're trained to sound human. They don't have common sense, they are trained to sound human. No matter how many LinkedIn life coaches, AI coaches tell you about it, I promise you they're just trained to sound human. These last 2 problems are a massive challenge for reproducibility. Reproducibility is a key it's a cornerstone of my job. If what I do is not reproducible, I might as well be doing astrology. No additional astrology, but we're not doing science if what we're doing is not reproducible. So going back to that statement, I would say that progress in modern astronomy is partnership between people and the right technology. And here the emphasis is on the fact that a new technology is not necessarily right by the virtue of being new. New technologies are opportunities for progress, but progress is not an inevitability. Just because it's new does not mean it's going to be revolutionary. Just because it was revolutionary in one area of science does not mean it's going to be revolutionary for you. We have to be as skeptical as we are passionate when we are scientists. We have to take these new models and stress test them, put them in difficult positions, see them fail, see where the limitations are. That's the only way for us to understand exactly how they work, exactly how they can help us, exactly how they can be the tools that bring us the discoveries of tomorrow. And then finally, adding to what the right technology is, understandable, reproducible, and I would say sustainable. Now, sustainability is a big question, but in general, the more computations you do, the more data you use, the less sustainable you are. Because data and compute require a lot of resources, electricity and real life resources. What's the word? Matière première. It's only coming in French. It's after 6 p.m. I'm really sorry. Materials that are really expensive, that have a human cost and an environmental cost. So when we're trying to solve a problem, we shouldn't jump to the biggest, most complex models. Machine learning is the last thing you do when everything else has failed. Machine learning has so much to offer, but it doesn't have to be used everywhere. All right, I'm going to end this talk with a few thank yous. First of all, thanks to Ken Smith, who is the server wizard who keeps Atlas afloat, and he's my partner in coding crime. A big thanks to my mentors, Stephen Roberts and Stephen Smart, in particular Stephen Smart, without whom I wouldn't be here today. It took 10 broad rejections, 2 years of not knowing what my next job was going to be, to actually land the job that I have today. And Stephen believed in me even when I didn't anymore. A big thanks to the Herschel Society for giving me the prize. Big thanks to the Royal Astronomical Society for hosting us tonight. And thank you for coming.
If you have any questions, please on the slides. Do you have any questions?
Thank you very much for a really engaging presentation. I want to ask about machine. We actually need to go back less than 2 decades to something like galaxies, where the reasoning was actually using could discern the signs between galaxies with humans. Clearly, machine vision's made huge strides since then. Has that completely overturned the situation? What's left for humans?
That's a really good question. Did people hear that online, or do I have to repeat it? Okay, brilliant. So Galaxy Zoo actually helped train some of the algorithms that work well today. You don't get, even when machines get better than humans, it's only because humans were there first. Let's not forget all of the citizen scientists that have put a lot of energy into that stuff. And I think humans still have a massive role to play, because where the algorithms fail catastrophically with these unknowns, humans are much better at making less poor decisions when they are faced with very new things. So in anomaly detection, for example, it's much better if you have something that looks really super weird, or you're really not sure, those gray areas where you're like, oh, it's not performing very well, show it to a human. We do that with the virtual research assistant. That's kind of how the policies are set. It's like, okay, below this this rank, I'm pretty sure it's garbage. We can put it in the bin. But there's things that I keep in there for a long time, for like 2 weeks. And if the model has not made a decision in 2 weeks, someone looks at it just in case. Most of it is garbage. Most of it is. But sometimes, it might not be. So there's plenty of room for humans. And when designing machine learning algorithms, the first question you should ask yourself is, where do the humans go in this pipeline? And what questions are they going to ask of the algorithm to trust what it's giving them?
Thank you.
Any question, please? How long did it take you to train the computers to get that level? And did you continue training them?
That's such a good question. So the question of how long it took to train the models is, in terms of like computations and putting the data and getting the results, literally seconds. It's especially the ones that I use, extremely fast. What took ages is finding exactly what models I was going to use, exactly what data, exactly how I was going to put it together. The design took 99% of the time. And then I ran the models, and then it started working. It was like, well, it takes longer to ask the right questions and calculate the right metrics than it does to run the right algorithm for the kind of stuff that I use. If you're thinking about generative models, it can take days. For the very big ones, it can take months. But we're not talking about that level of computing here. And yes, we do rerun them every so often.
Next question, please.
Are these models, if so, what is needed to, from a fairly basic starting point position? Is it something that an interested amateur can get involved in, or is there a lot of mathematics behind it?
So the models are open. The data. maybe I don't fully understand the question. I'm going to try and give a couple of details that maybe will elucidate this. So the models that I use are so specific to Atlas, and the data that it takes as input is so specific to Atlas that I wouldn't even give it as is to a colleague with a slightly different sky survey. I'd be like, use the method, retrain it, maybe retrain it based on my models, but you can't just, because the data look different. In terms of eyeballing, it's something that we do entirely in-house. It's very specific to our team. Even before the VRA, we just about had capacity. Now it's very much in-house, and only a small portion of the team that we don't need that much human input. But I know some friends, the go-to Sky Survey, for example, uses citizen scientists, and they use Zooniverse to do this. They've got a Kiloniverse Seekers project that people can get involved in.
Hi, I was wondering, are there still aspects of computational neural networks using AI that technology that you use in your work today?
So in Atlas, 100%, we use CNNs just before the VRA here. That's a pretty boring old school CNN. It's actually very similar to Lynette. That's the one that works the best for us because our images aren't super complicated. We don't have, they're black and white pictures, right? So the technology from the 90s works well for us. And then the number that I get from the CNN does go into the VRA as input because it is information. The VRA can't see the pictures, but by getting the number from the CNN, it's kind of giving that little bit of vision.
The steps, the algorithms, and
That's such a good question. We had that question earlier in the early talk. So the reason we can't do that is because the VRA uses as input, where was it? This stuff that the people can see. And in that stuff, there is information that we get at this step, the cross-matching step. And this information is really useful. That's part of why the humans make better decisions than you would do earlier in the stream. There's more information. But it's just so critical to the decisions of the VRA that it just wouldn't make sense to put it earlier in the stream. There's just, the info is just not there.
Thank you so much. Really great talk with you. You explained it so easily.
Thank you.
I have questions from online. When talking about running technology for astronomy, has it been any sector quantum?
So quantum computers don't work yet, and they're not going to work for a long time. But thanks for the question. They just don't work.
Technology is still good.
Yeah, and we do different kinds of calculations, which I'm not entirely sure are relevant to the stuff we're doing here. Maybe for really large scale models that need to do loads of calculations simultaneously, but for what we're doing here, not particularly needed.
So I'm curious to know, do you think that do you think all data?
No, absolutely not. We have complete control of the data that we get from the telescopes, and it is as raw and messy as you can get. It's pixels on pixels on pixels. There is definitely no AI going in for this stuff. I've seen a few papers of people thinking about using AI to denoise. Some of it looked not terrible, and I think there is plenty to do with. There's bits of generative AI that are not nonsense, that are not malarkey, that can be very useful. But at the level that we're working at, absolutely not.
I kind of managed to put on these for this industry. And the astronomy was always as set of data. I was saying I read the words in the just data you with that those types of
Sorry, can you repeat the question?
Is AI software with you look at this data? Would that be available to maybe just non-astronomers or young people who are trying to get into astronomy?
So I'm trying to think through the stuff that I know about that I don't know what, most things in astronomy are open and they're out there. Whether you'd actually want to use it, I'm not sure. I'm not sure it would be particularly riveting to be doing source extraction on really noisy black and white pictures. But if people want to do this, I know people who've got that code online. It's not that it's not user-friendly, it's why would you do this? Like, where is the blob? Essentially what we do is, where is the blob? Doing this day in, day out, maybe the first 2 times would be fun, but afterwards, I doubt how pedagogical that would be.
President Daniel on Zoom is asking, there are always black holes, neutron stars, and supernovas.
That's a very good question. In the high mass star supernovae, most of the time, yes. Neutron stars most of the time, black holes some of the time. There is a very weird kind of high mass star supernovae called the parent stability supernova, which can leave no remnant at all. It's a different physics of explosion, which is due to quantum mechanics. I'm gonna skip the details. I'm getting too excited. Basically, the star wobbles in weird ways and then suddenly just stops holding itself together and explodes, and that leaves nothing behind. But those are still, we've got a few candidates, but no confirmed candidates. We're still looking for them, and they would be extremely, extremely, extremely rare. So the high mass star supernovae most of the time leave behind a neutron star, sometimes when they're massive enough, a black hole.
Any more questions? I must say, the ones where you have the numbers that explains activity. And they have numbers that you could recognize.
That's exactly what we've got citizen scientists for.
Any more questions?
It remains me to thank Heloise for a tour de force of new techniques in astronomy. So exciting. And I think a round of applause for Heloise. And we will sit down. I'm expecting in the future to see your name on the gold medal, Dion.
Oh, well, let's wait a few days.
I believe there's is there a tour of the library for the exhibitors? Not today. Oh, sorry, wipe that. Thank you very much for coming, everybody. And see you again for the next public lecture. Thank you, Heloise.
Right. And